So imagine you have a list of numbers. It's unsorted, and you're looking to find an index of a particular number there, let's say 12. Classical computer science tells us that, well, the best you can do is to try. It's unsorted, so you cannot do any searches, and at worst, you will have to go through all of them. You're really unlucky. You always find your number as lost. Now imagine you take this gaming die, this six-sided thing that you use in board games, and you say, whatever it gives me, that would be the answer. This is useless, right? It just gives you random numbers. If it's a normal die, all numbers are equally probable. So you keep throwing it and it gives you random numbers, and you're saying, well, this isn't helpful. This is a quantum computer that is not calibrated, so it doesn't operate very well. And you did not program it well. You did not write a quantum program well enough. Now take a leap of faith with me and imagine this kind of magical scenario where you take the same gaming die and you slightly modify it. You maybe add a piece of material somewhere, like cut a corner, make one side more weighted, and you do it in a way that is somehow connected to the data, to that list of numbers. You still don't know the answer. It's not trying to trick this cube to go in the correct answer. You don't know the correct answer. But you know the shape of this list, you know some other properties, and you somehow make the cube different so that it's still random, but less so. It's less random. If you throw it multiple times, it tends to gravitate, to be skewed towards a certain number, which happens to be the correct answer. This is kind of crazy, like this doesn't make sense. But this is basically how a quantum computer that is well calibrated and well programmed by the programmer works. If you don't take anything else out of this lecture, take this. It's a very remote analogy, but quantum computing is basically trying to trick the universe in some isolated little piece for a very, very short period of time to behave slightly less randomly in a productive way that is useful to you when you solve some problem. So with that in mind, here's the plan. It's very thick, it's very dense. Buckle up. We start with quantum physics, we have to, but then we go into quantum computing, then into particular one kind of quantum computing, and then into its ecosystem and the full stack programming and Python. And hopefully, if gods allow, we'll do a short demo. This is an artist's rendition of a distant exoplanet with the coolest name ever, WASP-39b. It's about 700 light years away from Earth. For comparison, Jupiter is, I think, like 35 minutes away. So this is really far. It's so far that we have to look at this rendering, because if we look at the optical telescope, we at best see this smudge, like this pixel. You cannot see a planet. However, if you Google this planet, and many other exoplanets for that matter, you will find some publications where they say, wow, we actually found sodium, potassium, carbon dioxide, carbon monoxide, and different elements in the atmosphere of that planet. How? Like, you cannot see it. It's just a pixel, yet you know what kind of molecules are in the atmosphere of that planet. And the answer to the how question is spectroscopy. It's that thing that takes advantage of a peculiar property of some quantum objects. So scientists discovered this about more than 100 years ago now. If you take some atom, for example, this is sodium, it has 11 electrons, and you shine a light of wide spectrum, different, it's basically photons at different frequencies. Low frequencies, red color; high frequency, violet color. You shine the light through the through the atom, and you look at the light on the other side, and you notice that some parts of the light are gone. There are these black bars. And it turns out photons of a certain frequency got absorbed by certain electrons in that atom. The energy of that photon went into the electron and made the electron move to a certain energy position. Basically, got the energy from the photon, got excited. And as a result, the light on the other side does not have that photon. You don't see those colors. And this kind of looks like a barcode, and it is a barcode. It is a unique identifier, like a fingerprint of this material. Once the electron goes into that high position, it usually wants to go back down. When it does spontaneously, then it re-emits the photon of the same frequency. So later, you see another bars, which are like the inverse of those. So we have all those elements on Earth. So the scientists did this experiment for the whole periodic table and got like fingerprints of various elements. Now we have the database, and then they used multiple special instruments on the James Webb Space Telescope, and they caught that exact moment when that exoplanet was in front of its star, so that the light going from the star went through the atmosphere, and they looked at that light, and they found that bars in that light, and now they know what kind of materials are in the atmosphere. So this is amazing. And if we could simulate this, that would be great, because, well, not only to look at photons interacting with electrons, but if we could simulate any kind of quantum interaction like that on a computer, we could, design new drugs, new car batteries, agriculture elements, stuff like that.